Hi, this is going to be a series of lectures on double sequences and double series. I hope that I should be able to finish in 2 sessions, and the, we will end up with an application to the study of power series. We are going to prove a function defined by the power series is analytic in the disk of convergence. Okay, all right. So let us get started. So how do I define a double sequence? That's very easy, right? Recall, I define a sequence as a function from natural numbers to the set x, and by x1 we mean x value at n. Then we usually write the sequence x as xn, right? So how do you think I should define double sequence? Very obvious, just n cross n to x. Okay, or if you call it a, therefore a mn we denote by a. I should write as mn, but I will simply write as mn without putting a comma, right? It's not a at the product of m and n, but it is a the ordered per mn. Okay, right? Okay, this is kind of double sequence, right? So what we want to do is we are going to look at double sequences. Then a is called a double sequence. We usually denote it this by amn. This is called a double sequence. So like the way we figured out how do you write a sequence a, you write it as a1, a2, a3 and an, right? Therefore double sequence also you will write like that. We will write it as a11, a12, a13 dot 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 a1n and so on. Next, second row is a21, a22, a23, a2n and dot dot dot, right? And the mth row will be am1, am2, amn dot dot dot, right? All right, so this is the mth row, right? Now there are, see, since we already know how to define the convergence of sequence, okay, and the standard practice in mathematics to reduce the problem to something we already know how to solve. So we may be tempted to define, okay, the row-wise limits. Let's look at the sequence a11, a12, a1, and suppose this converges to, let us say, alpha 1, and similarly the second sequence converges to alpha 2, and this is the mth row sequence converges to alpha m, right? And suppose these sequences, suppose all these are suppose converge to alpha, right? These are all assumptions. Right? So how do I do that then? I am looking at limit of a m n. I am allowing n to vary first. This will gives me alpha m. Then I allow m to vary alpha m equal to alpha. Usually one writes this as limit n a m n. Suppose this converges, then I get a complex number. We are assuming these are all numbers in C. Okay. So forgot to say we will be dealing with our sequences n cross n or z plus cross z plus to C are real numbers. Okay, and this is over m. Now we can also look at another way. Look at this. I have the first column, which is a11, a21, a1m, am1. Therefore this first column, suppose it converges, suppose again assumption, so beta 1, and similarly this converges to beta 2, and this is n column, this converges to beta n. Yeah, then I can ask for whether this beta n converges to beta. Suppose this also, okay, assume. Then how will I write it? So limit a mn. Okay, what am I doing now? I am fixing the n, that is the second variable, and letting it vary over the first variable. Therefore I am taking the limit over m first. So what I am going to get? I am going to get a beta n. These are all assumptions. Assume that the column wise limits exist, and then look for limit as n tends to beta n. Suppose this also assume. Okay, then how will I write this? I will write this as limit over first over m, that is column wise a m n, and then row wise. Then you follow that. Then if this converges to beta, and this will say is alpha. Have you understood? Let's look at a very simple example. So what is the most natural question you can ask? Okay, one, a tentative definition. Okay, definition could be, okay, if we say AMN converges if alpha equal to beta. Oh, so notice that even though I wrote it simply, it means a lot of things. What is that? The row wise limit exists. I call it m through converges to alpha m, and the alpha m converges to alpha. Okay, so first row wise converges, and the limits alpha m also converges. Similarly, the column wise beta 1, beta 2, beta n converges, and the sequence beta n also converges to beta. So I am assuming a lot of convergence, right? And finally I am also assuming alpha equal to beta. Then I may say AM converges, but this is a wrong definition. This is a wrong definition. Okay, so let us look at. So this is something like, okay, you're defining continuity of function from R2 to R, right? You may say, suppose xy goes to, let us say, x naught y naught, then okay, I will simply say f of x fix 1, and then suppose y naught, this goes to f of something fix, and then for this is converged to f of x naught y naught, and similarly this limit exists. Are you following me? Hi, the system crashed, so I just have to, but luckily whatever I lectured, the initial part is saved, so let me continue. So a tentative definition, we said if limit, okay, or m and limit over n amn, that is a limit over m of alpha m equal to alpha, and similarly limit over n, limit over m am n equal to beta n, and limit beta n equal to beta. We said a tentative definition, okay, converges if alpha equal to beta. Okay, this we say is a wrong definition. Okay, why? Let us look at a function of two variables f of x y, f from R2 to R, right? Fix a point a comma b in R2. Okay, I want to say f is continuous R2 at AB, right? So since I know continuity of the function f, real valued function of a real variable, I may be tempted to say, let us look at, okay, something like this. This is my AB. Okay, I can say if look at this point and look at this limit as it goes this way and this way, they should be, if, okay, let me just say that. So one way would be limit, okay, x tends to a of f of x b, okay, equal to f of a b, and limit y tends to b of f of a y equal to f of a b, then f is continuous. This is a wrong definition, right? Because it only says as the points approach I have via this line or via this particular line. I mean, this may be like this. Are you following? So this is not a good definition, right? So similarly, this is not a good definition. So what? Okay. So what could be the correct definition? Let me just look at a correct definition. Could be, okay, we say AMN converges if there is an L in C, so that for every epsilon positive there is an N, so that, okay, for all M N greater than equal to N, mod AM N minus L is less than epsilon. Yeah. Right, now let's try to understand this. Means I have A11 and here I have AN1, I have ANN. After that what happens? So from this onward this will be ANN plus 1 and here it will be AN plus 1N and this will be AN plus 1. Okay, all these follows onwards. Okay, they should be within epsilon interval of L minus epsilon to L plus epsilon. Right? So starting from here and go all the way down, everything should be within this. Do you understand the picture? Okay. Now let's look at some so-called counter examples, etc., just to have an idea what kind of objects we are dealing with. Okay. Suppose let us look at this sequence. Okay, 1 0 0 0 and 1 1 0 0 0. Next will be 1 1 1 and here 0 0 0, right? And here 1 1 1 1, after that 0 0 0 0 and so on, right? So do you understand this thing? So what does it mean? You know, do you know how to define it rigorously? AMN equal to fix an M, then this should be 1 if my N is less than or equal to M, right? Yeah, M is 2, N has to be 2. If N is 3, yeah, N has to be less than or equal to 3. Do you understand that? As 0 otherwise. Okay, now you can see what are the limits row wise. Row wise limits are all 0 because these are all eventually 0 sequences. But whereas what are the column sequences? See, this is 1 all the way, except first this 1, therefore this also converges to 1 and this also will converge to 1 because these are eventually constant sequence. Therefore alpha in this case is 0 and beta in this case is 1 and alpha is not equal to beta. Okay, this is just to give an idea about such things. Yeah. Okay, now let's look at another thing. Suppose let us look at, so what we said, the row wise limit may exist, column wise limit may exist, and the sequence of row wise limits and the sequence of column wise limit, they also may converge, but the limits, the final limits alpha and beta need not be the same, right? Maybe you can wonder whether this is this convergent? Okay, this is not going to be convergent. Why? Suppose there is an L, okay, which is in C. Remember, these are all real numbers, therefore it should be, if at all the limit exists, it should be L. Okay, okay. If you want, you can take L in C also. It doesn't matter, right? Now let's look at L minus epsilon to L plus epsilon. Yeah, in the above case also I should have said, yeah, here it is. I assumed it's something like real, but this is L, then this is L minus epsilon. So after Mn, all my AMNs should lie here in this disk. Okay, yeah, right. Now do you see some problem? Suppose if I take epsilon equal to something like 1 by 3, the total length of the interval will be at most 2 by 3, strictly less than 2 by 3. But remember, if there is an n, okay, and let's look at nn. Nn will be 1. A n n will be 1, right? And what will be an plus 1? N plus 1, sorry, n plus 1, that will be 0. Remember, amn is 0 if n is strictly greater than m. Therefore, this is 0, right? Now, if there is such an n, then both should lie here, right? A and n must lie here. A and n and n plus 1 both lie in BL epsilon, right? But what is the diameter of this? That means, okay, ANN and AN plus 1, the distance is less than or equal to ANN minus L plus L minus ANN plus 1. That is less than epsilon and less than epsilon, right? Where epsilon is 1 by 3. Therefore, this is 2 by 3, but this is always 1. So, this is a contradiction. Yeah. So, pause, review, proceed. So what are the things we found out? We said that the so-called iterated limits, that is row-wise limit and column-wise limit, and the row-wise limits also converge, column-wise limits also converge. The iterated limits may exist. Okay, maybe I should use that word. The word is called iterated limit. Okay, take row-wise, then column-wise, and similarly column-wise, then row-wise. Okay, keep the geometry. This is your alpha. This is how. And the next one is you go this way. Okay, it may or may not converge. Assuming these are all converge. Okay, so they may exist, but still the sequence may not be convergent. Right. Now let's look at another example. Mn is minus 1 to the power m plus n by 1 by m plus 1 by n. Right. Now you can see if I take L equal to 0, the sequence Amn converges to 0. That's because you give me an epsilon positive, then what do I need? Amn in modulus. Okay, that is in modulus 1 by m plus 1 by n. Right? So if I choose an n so that 2 by n is less than epsilon, right? Therefore I can choose if m is greater than or equal to n and n is greater than or equal to n, therefore 1 by m is less than or equal to 1 by n, etc. This will be at most 2 by n, but that's less than epsilon. Right? Therefore this is convergent. So this double sequence Amn is convergent. Right? But the iterated limit does not converge. Why? Let us look at A1n, this sequence. Okay, what is A11? Minus 1 to the power 1 plus 1 by 1 by 1 plus 1 by 1, which is 2, right? And the next one will be minus 1 plus 2, this will be 3, therefore minus, this will be what? This is 1 plus 1 by 3, 1 by 2, right? Therefore it's going to be minus of 2, minus of, etc. So notice that, just let us look at more generally. I hope you all of you can make sense out of this. If I put am in, this is minus 1 to the power m plus n by 1 by m plus 1 by n. Okay, without this, if I fix m, okay, amn, I can say it converges to 1 by m. Do you understand this? Intuitively, if this term does not exist, absent, then fix an m, then as n goes to infinity, this fellow will go to 1 by n. But then now you can see the alternative nature. M is fixed, therefore minus 1 to the power m plus n, it varies with the parity of n. Right? Therefore, it's something like intuitively 1 by m minus 1 by m, etc. etc. but with a small 1 by n term adding. Do you see that? Okay, please work on this, understand and work out a proof. Write a rigorous argument. To show amn limit over n does not exist. And similarly, limit amn does not exist for the same reason. Because if you fix an n, okay, if you fix an n, then it is, where does it converge to? It converges to 1 by n without this term. Therefore, it's something like alternating. Yeah? Okay. So, what have we seen now? We have seen that, okay, the first example we saw that both the iterated limit exists, they are not equal, and the sequence is not convergent. In the second case, what we saw was the double sequence converges, but even the row-wise limit does not exist. Leave alone whether the sequence of row-wise limit converges or sequence of column-wise limit converges. Okay, even the row-wise limit do not exist. Similarly, column-wise limit do not exist. You follow that? Okay, these are all some examples, but whenever you learn this kind of thing, what is more important, because I know a lot of teachers and students get enamored by the so-called counter examples. But in real life, what is going to be more important? Counter examples are important. It just tells you why the hypothesis of various results are have to be checked. That's why they give counter example, right? But when you want to apply such results, the so-called positive results will be good. Meaning, under certain extra hypothesis, there is some positive result you can conclude. That is very important. This may be vague, but let's look at some theorem. So the theorem says the following. So let amn be a double sequence. Assume that the limit m over amn exists and limit n over amn exists and limit over mn amn exists. This is the limit of double sequence, right? Then all the limits are the same. So sorry, not all the limits are equal. Okay, so let us say equal to this is alpha, this is beta m. Yeah, I am leaving. This is alpha m. Okay, then limit alpha m equal to limit over mn of amn and equal to limit beta n over n. Okay, what I am assuming, please understand. In the last example, we saw the row-wise limit does not exist. Leave alone the convergence of the sequence of row-wise limits, right? But what we are now saying is assume the double sequence converges and the row-wise limit exists, then the sequence of row-wise limits will converge. And where does it converge to? It converges to the limit of the double sequence. Please understand. It's very important to understand the result. Okay, so what we are assuming is, just if you want to look at the picture, this is am1, am2 and amn. Suppose this converges to alpha m, then we are saying this should converge and will converge to where? It will converge to limit of amn. This is a double limit. And similarly the column. Okay, please understand, pause, review, proceed. The proof is easy. Proof is easy. So what is that I have to prove? Let alpha m equal to limit over n of amn. Then we have to prove and let L equal to double limit. This will always write as this way. We will prove alpha m converges to L. This is what we want to prove. Right? So let epsilon be given. Then what is that I want to estimate? I want to estimate alpha m minus L. Right? But remember, what is alpha m? That is the limit of amn. And what do I know? amn, the double sequence converges to L. So what does that mean? Since amn converges to L, okay, for this epsilon, okay, there is an n, so that m is greater than or equal to n and n is greater than or equal to n. That implies amn minus L is less than epsilon. Right? Now this is fixed m. Okay. Now what do I have? I have a sequence of numbers, that is am1, am2, amn. If you want to call it as b1, b2 and bn. What are we showing is these things converge to L, right? Therefore beta 1 converges to L. But what does that mean? Are you following? Therefore fix an m and let n tend to infinity, then this is nothing other than your alpha m. But since it's in the limit, I can only write less than or equal to epsilon. Do you understand that? So please follow. Then this, you are fixing m and letting n tend to infinity. But then what do I know? amn goes to alpha m as n tends to infinity. Right? That's what you are writing. So if beta 1, beta 2, beta n converge to L, and if beta n converge to, sorry, b1, bn converge to b, then what do I know? Bn minus L is less than epsilon. Okay, for all n greater than or equal to capital N, that will mean, okay, since the limit is there, b minus L will also be less than or equal to epsilon. Okay, this you know, right? If also this also follows by, just an aside, just you have to keep thinking. This is also continuity of absolute value function, right? If xn converges to x, mod xn converges to mod x. All right. So what do I know? Bn converges to b, and okay. Let us look at the function bn. So function is mod bn minus l. Okay, that is less than epsilon. Therefore, mod b minus l is less than or equal to epsilon. Okay, is it clear? And this shows what? This shows for every m greater than or equal to m, alpha m minus l is less than epsilon or equal to epsilon. This implies alpha m converges to L. And similarly, beta n converges to L. Do you understand the proof? Yeah? Pause. Review, proceed. These are all very easy. Once you have understood sequences, okay, some slight care, you will get all these results. Now the next thing, suppose I have a sequence am and double sequence amn, okay, and suppose it converges, limit over mn equal to L. Okay, now I have a sequence, the diagonal sequence. Do you understand that? A11, A22, ANN, right? So let me call it Bn to be ANN. Okay, what do you know about Bn? The diagonal sequence. this is a sequence of real complex numbers now, right? It's not a double sequence, it's a sequence, ordinary sequence. This also converges to L. The proof is easy, right? Why? Because I know this converges, therefore given epsilon positive, as usual there exists n, so that mn n greater than or equal to n. That implies mod a mn minus L is less than epsilon. Therefore, if I choose my n greater than or equal to n, then mod a n minus L is also less than epsilon. Right? This is clear. Okay. Pause. Review. Proceed. So now the next thing is, given a double sequence AMN, how to define Cauchy? When do I say this double sequence is Cauchy? Now that you know how do I say the double sequence is convergent, okay, it should be very clear. Remember the picture also I wrote? I wrote that you look at ANN, after that, okay, anything which follows below that, okay, to the right and again below, all of them should be within epsilon distance from the limit L. Now how do you think you will define Cauchy? We say it's Cauchy if for every epsilon greater than 0 there is an n natural number, so that for every m, okay, so what do I want? I want an m, okay, greater than or equal to I, which is greater than or equal to n, and n which is greater than or equal to j, which is greater than or equal to n. Then a m n minus a I j should be less than epsilon. Again, let's look at the picture. So what I need is there is an ordered pair mn, there is an ordered pair ij. Therefore, I have amn, I have aij, right? So, like a Cauchy sequence, what do I want? I want whenever m and n are greater than or equal to capital, mod am minus mod an is less than epsilon. Here, what do I want? I want the ordered pair mn, okay, and the ordered pair aj. So I want them in the proper order also. Okay. Are you following? I am not simply saying m and n should be greater than or equal to n and I and j should be greater than or equal to n. There is a slight subtlety in the definition. Just make sure that you understand. Again, let us look at a picture. I have a and n. I have a n plus 1. Sorry, a n n plus 1, a n n plus 2, and so on. And a n, okay, and little n. And then I have a n plus 1 n and a n plus 1 2 and so on, right? So after this, what do I want is I take anything here and anything here, right? So my m should be greater than or equal to I and j n should be greater than or equal to g, right? Are you following this? Make sure that you understand. Pause, review, proceed. Make sure that you understand the definition. This should be less than epsilon. Yeah. Are you following? Yeah? Okay. Oh. So you okay, right. Now the question I want to ask is, what is the next question I can ask? If a double sequence AMN is Cauchy, is it convergent? So if it is convergent, what should I do? Again, the idea is, we know if I give a sequence of complex numbers or real numbers, if it is Cauchy, it is convergent. That is what is called Cauchy completeness of RRC. So somehow I have to use the Cauchy completeness of C to prove if a double sequence AMN is Cauchy, then the double sequence is convergent. So what we do is we reduce it to ordinary sequence. How do I do that? Let me look at, as I did, Bn equal to Ann, I claim this is Cauchy. Why? Is this clear why this is Cauchy? If Amn is Cauchy, then this is Cauchy. Why? Because let us look at this is Cauchy, therefore there is an n, right? So given epsilon positive, there is n, so that whatever I wrote, okay, Mn, I will simply write greater than equal to Ij, and that's greater than equal to Nn. Okay, this is just greater than equal to in the way I define. Each x coordinate should be greater than the corresponding x coordinates, etc., etc., and similarly y coordinates. Okay, that is my way of ordering. Okay, now so if I take my a b n, so if my n is greater than equal to capital N, okay, and m is also greater than equal to capital N, then what happens? Bn is a nn and bm is a mm. Therefore, one of them is greater than, right? So let n equal to maximum of m and n, right? Therefore, the ordered per nn is greater than equal to ordered per mm. That is greater than equal to ordered per nn, right? Therefore, what do I know? Bn minus bm is less than epsilon. This is true for all m and n greater than equal to n, right? Hence, the diagonal sequence Bn is Cauchy. So let L equal to limit of a nn. Then we want to prove a mn limit the double sequence converges to L. Yeah. So what is that I have to do? Given epsilon positive, I have to estimate this a mn minus L. Yeah. But what do I know how to estimate? So what is L? L is the limit of a nn, right? So we use our Coriolis trick. What is the Coriolis trick? We will write it as a m minus some a k plus a k minus L, right? Now since amn is Cauchy, there is an n1, so that whenever mn, okay, and kk, suppose my kk is greater than equal to mn, which is greater than equal to capital N, this will be less than epsilon or epsilon by 2, right? Now since ann converges to L, there is an n2, so that whenever n is greater than equal to n2, mod ann minus L is less than epsilon, right? Therefore let n equal to this n1, maximum of n1, n2, right? Then what do I want? So now take, so let us assume mn is greater than equal to nn. Okay, again remember, greater than equal to my definition, little m is greater than equal to capital N, little n is greater than equal to capital N. That's my definition of greater than equal to there. Okay, take care to be maximum of m and n, right? And now let me assume m is greater than equal to n and n is also greater than equal to n, right? And where n is maximum of n1 and n2. You understand? Yeah. Therefore, this is kk is greater than equal to mn, that is greater than equal to capital N, and that's greater than equal to n1. You understand? Therefore, this will be less than epsilon by 2. Right? Now let's look at k, and k is maximum m and n. Okay, right? But maximum m and n, that both are greater than equal to capital N, but capital N is greater than equal to n2. Therefore, k is greater than equal to n, which is greater than equal to n2. Right? Therefore, this will also be less than epsilon. Therefore, we have proved this is convergent. Okay, go through the proof, try to understand. Okay, I'm not writing these things. Okay, so these are the basic facts we needed about. So this is, we conclude double sequences. Okay, so let us recall what we have done. So let us recall what we have done. We define what is meant by a double sequence. Then we define what is meant by iterated limits. Okay, then we said that take the row wise limit, call that all mth row will be alpha m if the limit, if the mth row, the mth sequence in the mth row converges, call it alpha m. Then let's look at limit, the sequence of row wise limits, the alpha m. If it converges, call it alpha sum. Okay, so notice that alpha m may not exist, and if alpha 1 alpha m also exists, that limit may not exist. Similarly, we can define column wise limit. Okay, that limit may not exist, and the sequence of column wise limit, that is sequence beta n, may not even converge. That limit may not exist. So even if they are equal, okay, the double sequence may not converge. Okay, we define the convergence of the double sequence. So the first important result we proved is, if the double limit exists and if the row wise limits and column wise limit exists, then the sequence of row wise limits converges and sequence of column wise limit converges, and they both converge to the limit of the double sequence, right? And another important result we proved was, we defined what is meant by a Cauchy sequence of for a double sequence. When do we see it? A double sequence is Cauchy, and we proved, if a double sequence is Cauchy, then it is convergent. Yeah, this is what we proved. The next thing is, we want to define double series. I will do a bit of that because I want to finish in 2 sessions. So maybe I can stop here. Yeah, okay.